Okay, so we've just seen that we can diagonalize a matrix using eigenvalues and eigenvectors, at least in the case that it has an n by n matrix, it has n different eigenvectors. So we don't always have that, but if we're lucky. So here's a matrix we want to diagonalize. Notice the eigenvalues are 1 and 2. They're different. So each one has an eigenvector, and we have 2 independent eigenvectors, so that's lucky, it should work. So the eigenvectors here are 1, 0 and 1, 1, as we've seen. So all we do is write down P and D. We don't have to kind of sweat this at all. We just put the eigenvectors we found as columns and call it the matrix P, and the eigenvalues we put on the diagonal. We just put them in the right order. So 1, 0 was the eigenvector for the eigenvalue 1, 1, 1 was the eigenvector for the eigenvalue 2. If you just pop that in, multiply by a, you'll see you get 2, 2. It doesn't actually matter what the t is, the multiple, so it would work just as well if we, doubled one of the columns. I mean, the thing is, it comes out in the p inverse, so it changes p inverse, but it still diagonalizes it. A special case, a matrix is called normal. It's kind of strange. It's not normal at all. It's quite special, actually. That's just the word that's used. A matrix is called normal if A transpose A equals A transpose. So it's a square matrix, of course, that we're thinking of, because otherwise we, this wouldn't make sense for eigenvalues and so on that we're talking about. But because usually A transpose A and A transpose are quite different. If A is symmetric, of course, A transpose equals A, and they're both just A squared, right? So normal is just a little bit more general than symmetric, and is a handy property. So it turns out for normal matrices, see, it's not normal at all. It's kind of pretty strange. If the eigenvalues are different, then the eigenvectors corresponding to those eigenvalues are orthogonal. So we knew that was true for symmetric, but it's a little bit more general. In that case, if we've got a full set of eigenvalues, then we've got this neat property that we can choose orthogonal eigenvectors, and if we also make them length 1, because we can choose the length, then it turns out that P inverse is the same as P transpose. So you can check that that's a property that in a matrix whose inverse is its transpose, then actually the columns are orthogonal to each other. So this is a neat thing that in that case we can diagonalize just using an orthogonal matrix. And in fact, you can think of these orthogonal matrices, they're really rotations and reflections rather than scaling things, because they just rotate the standard x, y, z axes to a different set of orthogonal and normalized length 1 axes. So this is a special situation, and of course, if we just make the eigenvectors length 1 and we know that they're orthogonal, then we don't have to work out P inverse by any difficult way. We can just take the transpose. So choosing eigenvectors correctly just means that we choose them so that they're orthogonal. So different eigenvectors are orthogonal, but we just choose the length to make them length 1. So we can divide by the length of any vector that comes out. So here's a matrix. Is it normal? Let's check. So if you do A transpose, it's the same as A, so it's actually symmetric. So in particular, it's normal. The eigenvalues here are -1 and +1. And if you go through that, of course, you just put those in. If you add or subtract 1 from the diagonal, you clearly get a singular matrix. The orthogonal eigenvectors, so the eigenvectors like minus something something and something something, the same. But if we want a unit vector, we want the length to be 1, say we started with 1, 1, as our example of an eigenvector, the length of that is square root of 2, square root of 1 plus 1. And so we divide by root 2 and we get a vector whose length is 1. And so in this case, P inverse is just the same as P transpose. And if we multiply this out with work, the eigenvalues are -1 and 1. So we've diagonalized it. It's actually a rotation through, I think it's 45 degrees one way or the other, you know, cos 45 degrees 1 over root 2. And it's really saying that this matrix just changes kind of x to minus x and leaves y alone. So it's a reflection. And then, so something like you rotate through 45 degrees, you reflect it, and then you rotate it back through 45 degrees. So it can help you understand what that matrix is. So our next thing we're going to do is understand another use for that, and that once we've got a ability to diagonalize a matrix, we can use it for fancy and interesting things to do with differential equations.